Beth.
And I'm Beth.
Welcome to Physics with
Beth and Beth.
Hello and welcome to Physics with Beth and Beth. I'm Beth. We're in this AP Physics C, the calculus-based curriculum. Engineering physics as well in college. Unit 2, Newton's laws of motion. And remember, this is just mechanics, not E&M. All right, so we're going to be talking about interacting blocks and third law pairs today. So remember, third law pairs. They are opposite and equal, and there can only be two objects involved. This is really important, all right, because a lot of times, if let's do a free body diagram. We know what those are. We've been working with those for a long time now in FBD. It's not a disease. It's just a depiction of forces that are involved. All right, I have a block here on my hand. If I put this block on my hand, how I'm going to draw my free body diagram is I'm going to have my normal force up. Can do it Fn or N, however you want to do it. And then I'm going to have a force due to gravity down. Now, in this case, yes, they're opposite and equal because it's at rest. The force, my hand is pushing up on the block. That's normal. The block is pulling down due to weight on my hand. Not third law pairs, though. That is three objects. And you're like, what? I'm only seeing one. Okay, there's the block, my hand, and Earth. When you're talking about the force due to gravity, that's the gravity field of the Earth. You've got the Earth involved. That's three things. You can't have three objects. All right, because here's the deal. On a free body diagram, we never ever put the forces that the object has. In other words, we only put the forces that are acting on the object. My hand is pushing up and Earth is pulling down. All right, but the block itself is pushing down on my hand when my hand is pushing up, and the block itself, as crazy as this sounds, as the Earth is pulling down on the block is pulling up on the Earth. Now, does it change our rotation patterns, or revolution, I should say, or our rotation? No, because this is so small, minor in mass compared to the Earth. All right, but so the third law pairs, if you were looking at the third law pair here, I would have my hand that is pushing up. All right, here, let me do this. I would have the force of my hand that is pushing up on the block, which would be equal to the force of the block, or this sign, block, whatever you want to call it, pushing down on my hand. Okay, this would be up and this one would be down. Opposite and equal. Then I would have a second third law pair that would be the force due to gravity, which is down, that's pulling down on this, and then it would be equal the force of this block pulling up on the Earth. All right, force of the block pulling up on the Earth is how we'll do it. The hand pushing up on the block pushing down on the hand, the Earth, and let's just call it, it's force due to gravity, the Earth, pulling down on the block, okay? So one more time. My hand pushing up on the block pushing down on my hand, one third law pair. Second third law pair, the force of the Earth pulling down on this block, and the block pulling up on the Earth. Kind of crazy. But we never put what the block is doing. We don't put these two on a free body diagram. So we end up with the normal force, that force of the hand on the block up, and gravity pulling down. All right? I just want to make sure you know that. That's a concept that's really important that they will test you on, and make sure you understand that before we even get started on these third law pairs. Now let's do a third law pair problem. It's the interacting blocks. We have three blocks here, a 1 kilogram, a 2 kilogram, and a 4 kilogram. And they're applying a 55 Newton force to this. All right, as you always know, free body diagrams is where you always start. Step one, don't ever try to do a force problem without a free body diagram. It will make your life, it'll just cost you time. Everybody's like, oh, it takes so much time to draw them. It'll cost you more time when you have to redo this if you don't get it right, okay? So here we go, 1 kilogram. I have force normal up for block 1, and I'm gonna keep those subscripts very specific here because we have three different blocks, three different masses, and I have force due to gravity down for block 1. I also have a 55 Newton force, a force of a push on this one. But now I actually have another force here. I have the 2 kilogram pushes on the 1 kilogram with an equal force that the 1 kilogram is pushing on the 2 kilogram. So the 2 is pushing back on the 1 is pushing forward on the 2. Okay, so this is the 1 kilogram. The 2 kilogram block is pushing back on it, and I'm going to call that a contact force of 2 on 1. Is how I'm going to do that, 2-1, contact force of 2-1. All right, those are the forces. Now this is going to be a smooth surface, and I'll show you what you would do if you also had friction, but this is going to be smooth right now, so we're not going to worry about friction. Obviously, all 3 of these blocks are moving to the east. I should have told you that. There's going to be enough force to move these. Now we're going to go to the 2 kilogram block. I have, again, force, normal. I'm trying to make it a little bit bigger here. That's a little too much. Force due to gravity 2. All right. Now, a lot of students want to go ahead and put this 55 Newton force on the 2 kilogram and the 4 kilogram, but you cannot. You're only going to put the force on the one that it physically touches. So only the first kilogram blocks is going to have that 55 Newton force. Now, these should be equal if I drew them kind of sort of equal anyway. Now I have on 2, 1 is pushing on 2 to the right, to the east. So I have this force of contact, and I'm going to try to draw them equal because we know that's a third law pair, opposite and equal. That's force of contact, but this time it's 1 on 2. There we go, 1-2. All right, that's what one block is pushing on 2. All right, well, the 2 kilogram block has another force. It has the 4 kilogram pushing back on it. The 2 is going to be pushing it to the east so that it all moves to the east, but the 4 is going to be pushing back equally. All right, so it has a force here, a force of contact of 4 on 2. That's a 4. That's really terrible 4. But anyway, that wasn't much better. Okay, now we need the 4 kilogram. We're almost done. You do a free body diagram for every object you have. We have 3. All right, this one's going to be the longest, force normal. 4, and by the way, we could have done F there. Then we have force due to gravity, also equal. Why am I drawing these equal? Because they're not moving vertically at all. It's only moving east. Now on 4, the only force it has, it doesn't have the 55 Newton force because it's not physically touching it. It only has the 2 kilogram pushing it east, and it needs to be equal. It's a contact force. And that's going to be 2 on the 4 block, and it needs to be equal to the 4 on the 2. Okay, now we have our free body diagrams. So again, 1 was pushing on 2, 2 was pushing on 1, 2 is pushing on 4, 4 is pushing back on 2. It's kind of like when the bug hits your windshield. It's equal and opposite force, right? The bug doesn't make out as well because it's got a lot less mass, but still. All right, now here's how you do these problems. You're going to sum them up as a system first. We're going to sum the forces in the direction of motion, which is in the x, equals mass. And when you do it as a system, really important here, you're going to be using total mass. All right? Now, why did I pick the x direction? Well, because it's all moving in the x, and I need acceleration, because what I should have told you is they want acceleration, and they want the force of contact of the 2 on the 1, and the force of contact on the 4 on the 2. So they want these 2 contact forces, and they want acceleration. So here we go. We're going to sum them up. We're going to do all of the forces in the x direction. All right, I have force of a push is to the east. That's positive. Minus this force of contact of 2 on 1. Then that's my only forces in the x on the 1. Now I'm going to go to the 2 kilogram. I have a positive force of contact of 1 on 2 minus a force of contact of the 4 block on the 2 block. I'm done with those. That's 2. 1 positive, 1 negative. Now I'm going to go to the last one, and I have a positive force of contact of the block 2 on 4. And that's going to equal the total mass, which is mass of the 1, mass of the 2 kilogram, and mass of the 4 kilogram, times your acceleration. Okay, we know third law pairs are opposite and equal. Opposite and equal they go. Opposite and equal, they cancel out. And I'm left with force of a push equals M1 plus M2, M2 plus M4 times acceleration. So if I want an expression for that, it's going to be M1 plus M2 plus M4. equals acceleration. And that would be an expression if they ask for an expression. If they ask for numbers, it's going to be 55 over 4 plus 2 plus 1, which is 7. So, well, I'll go ahead and put that in there so we don't skip that. And if you did 55 divided by 7, you get 7.86 meters per second squared. And that's your acceleration. That's the first part they wanted. Now they say, hey, find these contact forces. Okay, to find your contact forces, you're going to go to an individual block, which means individual mass. And you already know the acceleration. All right, it's 7.86. So I'm going to switch colors here so we can see this. And I'm going to go, here, let me draw a little box here. And then, ooh, that was annoying. Now I'm going to find this contact force of 2 on 4. But you're like, but that's not what they asked for. They asked for the force of the contact of the 4 on the 2 block. Well, remember, third law of pair, they're equal. I'm going to pick the one like least resistance, right? Like water always takes the path of least resistance. I'm going to take the path of least resistance here. I want to find that contact force. I know they're equal. This one has 2 forces in the x direction, and I don't even know what that one is, so I'm not going to be able to use that. This one only has 1 force in the x direction, so I'm using that. I'm going to do my 4 kilogram box here. And I'm going to do the sum of the forces in the x again, because that's the direction of motion, and it's only going to be on that 4 kilogram box. I'm not doing a total mass here. I have 1 force of contact, and that's that contact of 2 on 4, equals the mass of that block, which is 4, times its acceleration. Well, here, we'll put, let me not skip that. I'll do m4 times its acceleration. Okay, now I can plug in numbers. My 2 on 4, my mass was 4 and my acceleration was 7.86. So I get a contact force of block 2 on 4 of 39.3 newtons. And that's exactly the same as the force of contact the 4 is putting on the 2. Perfect. So I have done that. I've done that. Now all I need is my contact force of my 1 on my 2 on my 1 block, which is the same as saying the 1 on the 2. I can do it either way. I now know this number. This number is 39.3. I can find this one, or I can use this one. I'm going to go ahead and use the 1 kilogram. Problem strategy here. In the event I did some silly mathematical error here, then I'm going to get this one wrong too. But this was a given number, so I'm going to use 1 kilogram just to try to be smart here in my test strategy. So I'm going to draw another block, and I'm going to do the sum of the forces in the x, and I'm going to do it on that individual block of 1 kilogram. All right, well, it has the force of the push to the right. It has that force of contact of the 2 on 1, equals the mass, though, of only the 1 kilogram block times acceleration. So I'm going to subtract this expression over, minus mass 1 times acceleration equals that force of contact of 2 on 1. Now, I already know my force and my push. I know my mass, I know my acceleration, and I can find that contact force. My push was 55 newtons. It's a 1 kilogram because I'm only using 1 block. It's an individual block, not a system. My acceleration is still 7.86 because they're all staying in contact, means they all have the same acceleration, equals that force of contact of 2 on 1. And I get 47. The force of contact 2 on 1 is 47.1 newtons. All right, that is how you do a third law pair interacting blocks. We're going to do one more video on this where they're stacked. Instead of side by side, they're stacked. So now we're dealing with some normal forces and some additional force due to gravities. So that'll be the next video. Thank you for watching. I hope this clears things up. And we would love for you to subscribe if you're enjoying this, or sharing it with your friends if you're finding them helpful. And thank you for watching, and happy physicsing.